Thank you, Fatemeh. And first of all, I would start saying that I would like to thank Tony Rosato and Fatemeh Ahmadpour to have invited me to give this talk. It's a great pleasure. I'm sorry, I would have preferred to be there, but we have to be happy with this web presentation. So now I'm gonna try to share the screen. Give me 1 second, because I have to confess that I have 3 screens and I have to select the right one. Actually, with the pandemic, it's a great idea to have more than 1 computer. So in 1 computer, I'm running the faculty meeting. In the other computer, I'm working. Okay, so the title of my talk is, do you see it? Do you see the slide, right? Yes. It's Flutter and Divergence Instabilities and Hopf Bifurcation in Elastic Structures. So I would like to start saying that in the last 10 years, I did analyze several problems related with elastic rods. I have listed here some: configurational forces, penetrating blade, the torsional gun, the dripping of an elastic rod, the S-shaped constraint, elastic snaking, and so on. And I had a lot of fun in doing this. Today, this evening, for me it's evening, I will speak about fluttering rods, which is one of these topics, and I will tell everything starting from the very beginning of this story. And this is my research team, the people who joined me in this adventure on Flutter instability. Alessandro Cazzolli is a PhD student at my department. Francesco Del Corso is professor. He was my PhD student and now he is associate professor here. Oleg Kirillov spent 1 year visiting me, but now he is a professor at the Northumbria University in the UK. Diego Misseroni also took the PhD under my supervision and now is associate professor in my department. Giovanni Noselli is professor at Sissa in Trieste, and Mirko Tommasini was my PhD student and now he's an engineer, he's a consultant for an industry. So I would like to start from the first concept. First concept is self-oscillation and flutter. So the idea is the following. Flutter instability generates a self-oscillating system. What do I mean? I'm telling in a moment what is a self-oscillating system. It works like this. There is a steady input of energy. For instance, a steady wind or a steady flow of a liquid. And there is a system which takes the energy from these steady inputs and start developing a self-oscillation at a given precise frequency. So there are many examples of this concept. For instance, heartbeats, firing of neurons, ocean waves, the put-put boat, which is a toy. I'm interested to the so-called flutter instabilities, which are the oscillations of the Volgograd Bridge and the collapse of the Tacoma-Narrows Bridge. Then someone might say, well, the Tacoma-Narrows Bridge was not flutter instability, it was resonance. Well, of course, this is a little bit a point of view, but the crucial point is that the wind was more or less steady when the Tacoma-Narrows Bridge collapsed. So it means that we had a steady input of energy and the system bridge was able to create a motion, a cyclic motion of a given frequency. Of course, the bridge could not survive with this motion and it collapses. So the second concept I would like to introduce, now I'm understanding that probably I did a mistake. Forgive me, I have to relaunch the, sorry, 1 second, please, give me 1 second. Yeah, now we are back again. Do you see the screen, please? Yes, because, well, I don't want to tell you what was the problem, but we had a problem. So the second concept is that I would remind that Coulomb friction might induce instabilities in elastic systems. And we here now one of these instabilities is so-called thinking glasses. So friction is related to instability. The sound is an example of instabilities. There are other examples which are listed down here, and even the sound of a violin string, it's more or less an example of a frictional instabilities, because if you oil your violin, it will not play anything. My point is that usually these kinds of instabilities are related to the so-called stick and slip, or to the so-called negative slope of the friction velocity characteristics. So the thing I'm gonna to do is to refer to something simpler than that. I'm referring to dry Coulomb friction. The simple story which is told to students that if we apply a vertical load P, then we can slide a block applying an horizontal load which is mu P, where mu is a constant coefficient. So my idea is to use dry sliding friction as a source of instability for an elastic system. And now let's go to the so-called structural flutter. And we have to introduce the simplest structure showing flutter instability, which is the so-called Ziegler double pendulum. It is this simple structure. It's made up of two rigid rods. The two rods are connected through elastic hinges. We see one here with stiffness K2 and dissipation beta 2. We see another there, K1, beta 1. And so this is a 2 degrees of freedom elastic system, viscoelastic if you wish. And the peculiarity is the way that the load is applied. It's not a dead load, it's a tangentially follower load. It means that when the pendulum swings, the force remains always aligned with the final rod of the system. Well, with this simple structure, Ziegler showed that there are no quasi-static bifurcation, and he showed that a classical stability analysis fails to give a correct answer. And this structure has an instability, but is a dynamic instability, which is called Flutter instability or Hopf bifurcation by other people. And the onset of Flutter instability is given by a certain critical force P, and can be easily calculated. Eventually, it's this simple formula. So there is a range of forces corresponding to Flutter instability. And then if the force exceeds a certain value, we enter in another kind of dynamic instability, which is called divergence. So the difference between Flutter and divergence is that the Flutter, it's an exponential growth multiplied by a sinusoidal function. So it's a vibrational motion of increasing amplitude. We start seeing something flapping, and this flapping increases with time exponentially. Divergence instability is different. It's like slamming the door. It's simply an exponential growth. So this simple structure shows Flutter instability and divergence instability at certain critical values of load. So we have a sort of region of Flutter. This is the situation if the hinges are purely elastic. If we introduce viscosity, something strange, I could say very strange, it has been called paradox, happens. It happens that the Flutter load decreases, which is apparently strange, because if you would speak to an engineer saying, imagine a structure which has a certain critical load, then add to this structure a dissipation, the engineer would say, well, the critical load will be equal or higher. No, that's the other way around. It turns out that the critical load is smaller. This is something so strange that it has been referred as the Ziegler paradox, because if we calculate the structure for different values of viscosity, the viscosity predicts a lowering of the critical load. And then, to be complete, the paradox continues because there is something even more complicated. The story is like this. Imagine we solve the structure with the viscosity. And then we take the limit for the viscosity going to 0. What we would expect to find is the critical load of the structure without the viscosity. No, this is not true. Actually, we found a load which is inferior to the load of the structure calculated from the beginning without viscosity. This is very strange. It's so strange that many people believed it was wrong. And in particularly, Professor Koiter. I like him. I mean, he was a great scientist, probably one of the best mechanicians ever. But nevertheless, he was very skeptic about Flutter instability, Hopf bifurcation, and those things. And he wrote explicitly in one of his papers a statement which is reported on the Transparency, and we may see it. He wrote, "I propose the elimination of the abstraction of follower forces as external loads from the physical and engineering literature on elastic stability." So he was persuaded that tangential follower load could not exist, and all this story was a sort of mathematical exercise without any mechanical meaning. This was his clear point of view. He pointed out this on several occasions. Well, there were people who attempted some experiments with Flutter instability to demonstrate that this was in fact not, let's say, fantasy, but it was a real effect. One was George Herman and Nemat Nasser. They did some experiment with a fluid flowing through a nozzle, but in this case, it's not exactly the same thing, because if we let a fluid to flow through a nozzle, there are extra effects in addition to the follower load. There are hydrodynamics terms coming into play. So these experiments are considered to represent an instability, but not exactly the same thing as the follower force. Then there were other experiments done by Professor Sugiyama, who is a Japanese guy, he's an old person, and he did an attempt mounting a solid rocket motor at the end of an elastic rod. Well, we can have a look to an experiment. I have here a video of his experiment, so we can enjoy this video. If you want to attract the attention of the fire brigade on your lab, do that. So what we see here actually, it's the structure has this oscillation, which is probably Flutter instability, but please remember that the mass of the rocket changes very abruptly during the fire because it consumes. So people said that's not exactly a follower load because the mass is varying in time. And so we did our best to change this situation and to try to do something better. And the idea was to generate the Flutter instability using Coulomb friction. Apparently, this idea is very strange because people say friction is a mere dissipation. How can generate an instability which is a vibration of increasing amplitude? It looks impossible. In other words, imagine I tell to an engineer, I take a structure which without friction is stable. Then I add friction to the structure. Can this structure become unstable? Engineers usually say no, but we know that we have never to say no. And the final idea, it's in fact very simple. This is the sketch of the idea. We may see here the Ziegler double pendulum with the elastic hinge here and another elastic hinge there. Do you see my pointer, by the way? Hopefully so, yes. And the idea is we mount a freely rotating wheel at the end of the structure, and we force this wheel to slide with friction against an advancing plate at constant speed. So we move this plate down here against the structure, and since there is a relative sliding between the wheel and the plate, it generates a follower force, because if the structure is deformed, we can see that the force will always remain coaxial with the elastic rod. This is something that we thought so more or less 10 years ago, and we did the experiments, and we proved theoretically and experimentally that it works. We may see here the experimental setup, the Ziegler double pendulum. There is an accelerometer mounted on the end of the structure, the freely rotating wheel, and we have calibrated this system, measuring the elastic stiffness of the rotational springs, measuring the viscosity, everything, the coefficient of friction. And we have found that for small frictional loads, the structure is stable. For higher load, it goes into Flutter region, and for load even higher, it goes into divergence. And the experiments, the movies of the experiments are shown down here. On the left, the force is small and the structure is stable, and so it remains straight. At the center, we see that the Flutter instability, so the structure starts oscillating. This oscillation reaches a limit cycle very soon, and so it becomes a self-oscillating structure. And this is the situation of Flutter. Finally, on the right, we see the situation of divergence, where it is like slamming the door. You may wonder where there are these ugly black rubber on the right, on the left. I can tell you that the first time we ran this experiment, we broke everything. And so we said, why don't limit the movement of this guy? And we added this little constraint. This was the situation up to 6 years ago or so. But we wanted to do more, and particularly we wanted to analyze an elastic continuous system like this. We see here an elastic rod. It has a concentrated mass on the end, and it is subjected to a follower load P, which actually has a degree of follower. I mean, it is inclined with respect to the tangent of an angle, at an angle that we can change and modulate. Well, the equation governing the linearized kinematics of this structure are standard, and so the Flutter, the follower load, enters only as a boundary condition and is sketched down here. So these are the equations. This is a known system, has been solved some 20 years ago by De Tinco, a Russian scientist, who was able to calculate the Flutter loads analytically. We can do all this. But the problem is, are we able to design a machine to analyze, to induce Flutter instability in this structure, exploiting the friction of the system? Well, that was not an easy stuff, and I can tell you why. There are two reasons. We could not adjust the old system for these new experiments for this reason, because we used the original structure as a lever. So to change the tangential load here, we had to change the vertical reaction, and to change the vertical reaction, we were changing the vertical load here. This can be done with a rigid structure like this, but if the rod is elastic, then we have torsional buckling for that. And if we use a circular rod where the ellipse of inertia is a circle, then we do not have lateral buckling, but we do have large deformation to get the correct force. We have to deform a lot this rod to get the right vertical force. This was one problem, more serious than it may appear. And the second problem was that with the original machine, experiments were only taking few seconds because the stroke of the machine was half meter, and then the experiment was stopped. So we wanted to continue experiments as long as we desired, and so we designed a completely new machine for experiments, which is sketched here. First of all, the load is directly applied at the end of the beam, on the head of the beam. we have a head here, we have the little wheel which is freely rotating, so friction is transmitted tangentially, but to apply the vertical load we have a glass plate which is pushing against these pressors which are almost frictionless, and in this way we give directly the vertical load to this element. And the second problem was solved because now it is not a machine with a stroke, but is a conveyor belt which formally has an infinite stroke. It can go forever. So this is the idea of the machine. And let's see how we have realized this machine. Actually, we see a sketch of this. White is the elastic rod. Then this is the head with a detail of the head. There is a miniaturized accelerometer on the head. There is the freely rotating wheel, a miniaturizing loading cell measuring the tangential load that we are transmitting to the rod, then the pressors, and this is the equipment. We can change the vertical load hanging a given weight. This is what we have realized, but we have spent a lot of time in the calibration of this machine, trying to measure everything. For instance, what is the vertical transmission of load to the head of the elastic rod, or what is the exact inclination of the transmitted force to the elastic rod, or what is the exact friction rule, because we know that the Coulomb friction is only an approximation, and so we struggled in the technique experimentally with independent measures the correct frictional force at the wheel. And then there were other 1,000 things. For instance, we had to determine the correct dissipation of this system due to the internal dissipation of the elastic rod and due to the air drag in which the rod is moved. So eventually we can see an experiment, and this is the result. On the left we see the experiment in the stability range. On the right, the abacus simulation where we have implemented all the features. This is Flutter instability. We see the motion of increasing amplitude, and it reaches a limit cycle, and this is divergence. Actually, the difference between Flutter and divergence is more or less the frequency of the phenomenon. The divergence instability has very low frequencies because it's like slamming the door, but since the door has to arrive at an end, then it goes back because it cannot do anything else. And so eventually we still see a fluctuation, even if the linearized equation provides us an exponential growth, and that's it. So these experiments were all instrumented with, we have measured almost everything, and these experiments led us to the conclusion that I'm showing in this video. So the curves on the left are the theoretical curves. Don't ask me because the curves are broken, because they are actually not broken. Is that we have superimposed different curves relative to different zones of the graph. So there is no discontinuity in reality. But the yellow dots are the results of our experiments. So it turns out that we have not only investigated Flutter instability, which is the broken curve on the bottom, but we have also analyzed the divergence instability occurring at higher level of load, and it's the yellow stars here. And what I can point out is that all these experiments which were measured represent the first experimental proof of the destabilization paradox. We have been able to demonstrate that the inclusion of dissipation yields a decrease of the Flutter critical load. This we were able to prove. So now we may enjoy for a second, taking a break, and I would like to ask you, how many experiments do you think we have done? Because, well, you see one nice movie. Well, you may say, well, they did some experiments. Maybe we did many, or maybe we did a huge number of experiments. What do you think? How many? Well, this is the answer. We did at least 700 experiments. It took 5 years, and one PhD student really became mad in doing all this. 700 experiments without taking into account damping, identification, frequencies, divergences, slow motions, and blah, blah, blah. Okay. So up to this point, we have seen how to use friction to create a follower force. Actually, it's dry friction to create a follower force. And now I would like to go into a related problem. People studying Flutter instability know that there is another structure which is very simple, is as simple as the Ziegler double pendulum, which evidences this Flutter instability. Is the so-called Reut column. This guy, Reut, was a Russian scientist who lived more or less 100 years ago. And he solved the problem that we see here on, in the screen. So we have again the two rigid rods, again connected with two elastic hinges, or viscoelastic if you wish. But there is this element which is orthogonal to the last rod and is simply a rigid dead element, a rigid bar. That's it. And the interesting thing is the way that the load is applied. Please, the load is done in a way that it has to remain always on the same line. So it's not a dead load, it's another story. Actually, it's a non-conservative load. Initially, when I saw this structure the first time, I thought myself, well, this load, it's nothing strange. It's a dead load. No, this impression is mistaken. It's not a dead load. It's a very strange load, which is a non-conservative load. It remains on the same line. So when the structure deforms, it moves along this rigid element, but remaining straight and moving forward and back on the same line. So we can end up saying that with the Ziegler double pendulum, we have different possibilities. One possibility is the Ziegler load. We said it's a force which remains coaxial with this element. Another possibility is the dead load, the easiest thing that we can do. We have a force which remains horizontal, but it moves together with the structure. And we have here other two possibilities. One is a contact force with a smooth device. For instance, imagine we would like to put a load on it, a vertical load with enjoying gravity, exploiting gravity. Then if the contact is smooth, the force is orthogonal to this element. It's a contact force, which is conservative, of course. And the other possibility is the Reut load. The Reut load remains horizontal. So we have these four possibilities. And the four possibilities corresponds to the equations I have written before. We see that the load, the dead load and the Reut load, it's the same force, but one remains on the line, the other moves together with the structure. And we see that the other two loads are apparently different, but in a linearized context, they become the same. But the difference is that one remains horizontal and the other turns with the structure. Okay. Linearized dynamics. These are the equations of linearized dynamics. They are simple. It can be done to students. I'm teaching this stuff to undergraduate students. It's not difficult. It's a couple of differential equations, linear, which can be solved by hand. So the four situation of loads, they are different only because of the term of the load. So the rest of the structure is the same. So the acceleration of the masses remains the same. The damping is the same. The stiffness, the elastic stiffness is the same, but the load changes. So we have the dead load, the Ziegler load, the contact load, and the Reut. The important point is that both the Ziegler and the Reut are unsymmetric. They break the symmetry of the system, the symmetry of the matrices. And we may see that the dead load and the contact load are symmetric. So Ziegler and Reut break the symmetry. If we see this formulae, we may conclude that the Ziegler and the Reut are different, because actually the Reut load is the transpose of the Ziegler load. Yes, they are different and the dynamics is different, but all the behavior of the structure in terms of Flutter, divergence instability, Ziegler paradox, everything is the same. So it has the Reut and the Ziegler loads have exactly the same Flutter load, exactly the same divergence load, exactly the same Ziegler paradox. They are different because the dynamics of the system is different. We see them moving differently, but the instability picture is exactly the same. And now we arrive at the problem. It's always the same problem. Professor Ziegler says it is always the same problem. How to provide the Reut's load? We said that the Ziegler load is difficult. Well, it is also difficult, the Reut load, how to do. But we have the experience of Flutter. Again, we have attempts done by George Herman, Nemat Nasser, and Sugiyama. In this case, they didn't try with rockets, I'm sorry, but they used an air jet impinging the structure, which again, it turns the problem into a problem of aeroelasticity. It's not the same thing. So how to produce this force is again exploiting friction, but in a different way. Now we have, instead of having a wheel mounted on the end of the structure, we use a freely rotated cylinder on which the structure has to slide. Maybe this picture is not perfectly clear, but I can show you a detail of the experiment. We see on the left the Ziegler double pendulum. We see the rigid part is white, there's other rigid part. The elastic hinge has been done with a piece of carbon fiber, and the element here is rigid. And now how to give the load is that this structure has to slide against this freely rotating cylinder. So the cylinder is free of rotating through the axis, but is forced against the structure, transmitting a frictional force which remains aligned with the axis of the cylinder. So the frictional force remains acting along the cylinder. This is the trick of this realization. And now this is the way we adjust the machine we had to perform the experiments for Reut's column. We see here the Reut column from the above. Again, we have given the load with the glass plate we had prepared before. We have to force this cylinder to slide against the structure, and this is done with this actuator, which was obtained turning down a loading machine. We see here other details, and of course everything is instrumental. Now, first of all, I would like to show you a simulation of this structure. So this is the Flutter instability as the equations tell us, the nonlinear equations. So we have integrated the nonlinear equation. So this is the Flutter instability of the Reut system. We see that the dynamics is different from the dynamic of the Ziegler double pendulum, but the critical load is the same. And we may see that the force remains on the same line. It goes up and down, but it remains on the same line. The system reaches a limit cycle, and so this is a Hopf bifurcation, and the system is self-oscillating. This is the theoretical view. And now let's have a look to the experiment. We see it mounted from the above. This is the experiment. We are forcing the cylinder to slide against the structure, and we see that it oscillates with a constant amplitude. So initially the motion grows, and then it stabilizes and reaches a limit cycle. So it is becoming a self-oscillating system. The input of energy is steady. We are moving this cylinder, we are forcing the cylinder to move, and this is the situation. And now I would like to move to the divergence instability. This is the simulation with the nonlinear equations. This is like slamming the door. There is no oscillation. It's an exponential motion which goes to up to infinity. And now the experiments. Please notice that the experiment is terminated because the structure exits from the above glass, and so we had to stop immediately before everything was broken. So this is the experiment. Now it is out of the glass. So this is divergence instability. And again, the message is the same. Even in this case, we have been able to demonstrate that the Ziegler paradox is not a paradox at all, but it's an answer, a real answer of a real mechanical system which behaves this way. So the dissipation has a detrimental effect on the Flutter load and changes the Flutter region. And now I would like to come to the end of my talk with the last concept, which is the last one on this story. We grasped this idea a few years ago, and now we have reached some conclusion. The idea is the following: is it possible to get rid of friction? Because one can say, well, what does it happen if the road, if the wheel at the end of the road cannot slide? I mean, it is a wheel which only rotates without slip, without any slip. Well, this is called a non-holonomic constraint. We see here two examples of non-holonomic constraint. It's a wheel, as I said, rotating without any slip, and it's a skate, a perfect skate, let's say, that goes in one direction but cannot go in the orthogonal direction, cannot move. Well, non-holonomic constraints are applied to the velocity, not on the position. What does it mean? Well, take the skater. The skater can do, can reach every point in the plane. The lady skating can go everywhere. It's not, there are no forbidden position. But the non-holonomic constraint says the skate can only slip in the direction of the skate, and then you can go around turning and doing things. So it's not a constraint on the position, it's a constraint on the velocity. That's it. This is the essence of the non-holonomic constraint. And the easiest of this constraint is exactly the non-slipping road, the skate, the perfect skate. Can we use this constraint on our structures to find instabilities like Flutter or divergence or the Ziegler paradox? Because one might think, what does it happen in the experiments before if I forbid sliding? Because the friction is so high that it cannot slide. Well, we may see that perhaps something strange is happening now, because until now, Flutter instability has always been related to non-conservative loads. And we can see here a little collection of statements, but there is a long list. If you would go to visit one of my colleagues in Italy, they would already old enough to know what is this topic, because many young people don't know Flutter and this stuff, but the old people do know. And so if you ask them, they will say, oh, Flutter is only possible with non-conservative loads. And here we have a collection of statements. Elishakoff, Bolotin felt, if my memory serves me well, that it should be impossible to produce Beck's Coulomb experiment via conservative force. Anderson and Dawn, sometimes the creation of a force like a follower force in the laboratory presents awkward practical problems, and the simulation of this force, wherever possible, by a conservative force would be very convenient. It would be convenient to do it with a conservative force. But because of the different nature of the fundamental properties of the conservative and non-conservative system, the simulation could only work in a situation where the two systems behave in similar ways. That is when the conservative system is not operating in a regime of oscillatory instability. The conservative system cannot become dynamically unstable, since by definition it has no energy source from which to supply the extra blah, blah, blah. So no. And then Koiter again, it appears impossible to achieve any non-conservative load condition in the laboratory by purely mechanical means, because non-conservative external load always require an external energy source, much as blah, blah. And Singer was a non-experimentalist in buckling and instability. An example in the field of elastic stability of what Drucker referred to as playing useless game. So non-conservative forces are useless games, okay? But the problem is like this: if we find Flutter instability, if we find Hopf bifurcation, if we find Ziegler paradox, divergence instability with non-holonomic constraints, well, holonomic constraints do preserve energy. And so what? The non-conservative forces are not there. So we can find, the question is, can we find these critical loads, these effects with non-holonomic constraint? If the answer is yes, then we are getting rid of the non-conservativity of the loads. So we invented these systems. Actually, these systems are the same you have seen before, but now there is no slip. The wheel can freely rotate, the cylinder can freely rotate, but without slip. Slip is out of the equations. It is an holonomic constraint. We did it for the Ziegler double pendulum, and we did for the non-holonomic Beck or Reut rod. We analyzed all these cases, all these situations. It turns out that a viscoelastic column subject to the skate or the violin bow, we called these two non-holonomic constraints. One we called skate because it looks like a skate. The other we call it violin bow because it resembles a sort of violin bow. So let's start from the beginning again. A viscoelastic column subject to the skate or to the violin bow constraint, and the same structure subject to non-conservative loads of the Ziegler or Reut type evidences exactly the same critical loads for Flutter, Hopf bifurcation, and divergence, and the same Ziegler paradox with the same directionality dependence occurring when multiple sources of dissipation are considered. So I'm saying this: the linearized version of the non-holonomic constraint shows exactly the same behavior, exactly the same equations as the non-conservative structures. So we have found an equivalent of the non-conservative loads obtained with non-holonomic constraint. And these are the examples of the structures that we have analyzed. So please, on the right end of the structure, there is the skate, so a wheel we cannot slip. And on the right, we applied a dead force. I'm sorry, it's not clear. No, sorry, it's not a dead force. On the left, we are compressing a spring, a linear elastic spring, until the structure becomes unstable. So the way of loading this structure is conservative because it's squeezing an elastic spring. And on the right, we load the structure with a dead load, like a stone in the gravity. So on the left and on the right, we have two ways of loading these structures, which are fully conservative. So in these systems, the energy conserves. And what we do see, we see a Flutter instability, and we see that the system reaches a limit cycle. So we found the Flutter instability, the Ziegler paradox, Hopf bifurcation, limit cycle, and these systems are conservative. And here is a sketch of a solution. We see we are loading with this dead force, this double pendulum, with this non-holonomic constraint, no slip, and we see that the structures start oscillating, reaching a limit cycle. We see it on the right. So the motion is amplified, and then it reaches the limit cycle typical of the Hopf bifurcation. And on the upper row, we see the Ziegler configuration. On the lower row, we see the Reut configuration. We actually does the same thing. It oscillates about a constant mean velocity and reaches a limit cycle for a system which is fully conservative. And now I'm going to show you a couple of movies of simulation, how these structures behave. This structure is loaded with a dead horizontal force. It is sketched horizontal, but you can imagine it vertical with a load, with a stone put on it. So this is the behavior. It has this Hopf bifurcation, critical load, etc., Flutter, everything. It behaves like the Ziegler double pendulum, at least in the linearized version. When the displacement becomes large and the non-linearities prevail, then the two systems become different. But initially, they behave exactly the same. Then the question is, where does this energy come? That's the solution, is simple. The load that we see on the left can continue to push the structure up to infinite. And so it's a continuous steady source of energy, even if it is conservative. It's like to say that we start from 1 kilometer in the atmosphere with a stone, and we go down with this stone for 1 kilometer, the structure reaches a limit cycle. So on the right, we have the Reut type of loading, so-called violin bow. Again, here we have a similar behavior, not exactly the same, but the similar. I'll play this again because for me it's a great pleasure to see these movies. I have seen millions of times. And now the other way that we can load this structure is compressing this linear elastic spring. So we compress the spring up to the point when the force in the structure touches the limit value. At that point, the structure moves and dissipates the elastic energy. So in this case, we do not reach a limit cycle because it cannot be reached, because there is a fixed amount of energy which goes. So let's have a look. Initially, we see only the spring moving. Now it's only the spring moving, compressing up to the critical load, and then the structure starts oscillating and the energy is dissipated. Yeah. I'm coming to the end, and so I would like to thank you for your attention. You have been so kind to invite me to give this talk. I hope that you are not tired now, and thank you for everything.
Thank you, Davide, for the great talk.